Good afternoon. This is going to be a very short session because Dr. Kant has already covered the joint model. I'm just going to show you a little bit more in terms of the CD4 data so that things are a little more clear because how they have looked at the CD4 in terms of the joint models, and then we will do the practicals for the all the remaining. Okay, so what I'm just talking about the CD4 count here. Here, if you see that you have CD4 measured at 3 time points, right? So let's say this is for one individual. So at the baseline, the CD4 count is 650, and after 6 months it is 590, and after 12 months it's 500. So if you understood how the time dependent model is, so like we already mentioned that between 0 to 6 months the CD4 count remains at 650, right? Only at 6 months you have a reduced CD4 from the 650, it goes to 590, right? So when you draw a step function, okay, how does it actually look? So basically you have 650 at time 0, then it goes down, and then again it remains the same till the 6 months, and then comes down, and then again remains same till 12 months, and then comes down. It's like a step function, right? Like, so that is what the time dependent covariate, what it does is it only takes the one. So suppose the event has happened somewhere after 12th month, right? So the model, what we usually saw so far, except the joint, is that it will take the one which is the closest to the event that has happened. Okay, so that is how it assumes into your model. Okay, so which is not true, because you have actually not taken into account the progression of the CD4 for that individual is not taken, but only looking at the last time point is what you have considered. Let me go again to another example. So here, if you see this here, so a patient's true CD4 decline, actually suppose you measured it in reality, and that has gone from 650 to 600 to 560. That's the true CD4 count that has been measured for the patient. But what we actually see in a clinical study is only those 3 time points. Okay, somewhere those 3 time points, and what you have is only 650, 590, and 500. But you have actually not captured the whole progression of that patient by the time points that you have measured, right? So that is what you end up if you don't do a joint model, because I'm going to tell you how the joint model looks at it when you model. So what happens in your time dependent is, this is what it is. So here you're forcing it to be across all these time points. Instead of 600, you still assume it to be 650, right? Similarly, instead of 560, you assume it to be 590, because you don't take into account that reality of the reduction that is happening in the CD4 count. This is how usually the step function works, okay, in any model apart from the joint model. So let's now look at, okay, this is just a small example. I want you to calculate the survival probabilities. So just 5 subjects. Can you help me do this one? So what is the first probability at what time? Yeah, what is the first survival probability at time 0? Let's say that. Yes, so everybody is alive, so it's 100%, right? Or probability is 1. Okay, so that's why you always start with 1 on your uppermost this thing, right? Then what is now, where is the event which is happening? At 14 weeks, okay, 14 weeks or 14 months, sorry, months, okay. So at 14 months, you have the first event that has happened. Now, what will be your survival probability? 4 by 5 into, because he has already survived the previous time point. So ideally, it is into 1, but it really doesn't make, so it's only 4 over 5, which is 80%, right? Okay. What about the next one? At 15 months, you have the second event which is happening. So therefore, you have a survival probability which changes at the week 15, right? Okay. How much is it now? 3 by 4 into 0.8. Okay. So that's what we have done here. So if you look at this, but what is it if I want to calculate what is the probability at 18 months, then what will it be? Because that's censored, right? So it remains stable. Okay, that is what, if you remember, there is no event. When there is an event happening, only your survival probability will reduce. But when there is a censoring, it will just remain like that. So that is what is the step function. Okay. So what you are assuming is when there is a censoring happening, your probability remains the same. But that may not be true, right? So that is what we are trying to see in terms of how we do this. So here I have a data where I have 5 individuals. Okay, the same 5 individuals for whom you calculated the survival probability. But ideally, you see, can you tell me what is happening with these 5 individuals in terms of the CD4 count? Everyone's CD4 levels are coming down. Yes. So who is doing it more worse or who is doing it better? Who is worse and who is better? 4 is doing very well, right? So is that right? Because if you see the CD4 count in the drop, it's only about 10 units that you see for the patient 4, right? Or the participant 4. But when you look at what about participant 3 and 2? 2 is the worst, right? So what I have done is one simple way to assess this is I just did a regression, okay, linear regression. Simple way is I said what is the month change in terms of the CD4 for each individual. And what I have found this year is that I have for the first ID, it's about a drop of 6.7 units. Do you understand this one? This is a simple regression, right? With the time on the x-axis and your CD4 on the y-axis. We are just trying to see for patient 1 how much is the reduction in the CD4 count. Okay, so that is 6.7 units, around 7 units reduction. But as you said, for ID 2 and for the participant 5 and 3, the reduction is quite a lot. Okay, but when you assume a step function, you did not look at any of this reduction that was more for the patient 4 or more for the patient 2. Okay, so that is not captured when you do a time dependent because you're assuming it to be the same for all the individuals, right? So that is what we do it in a joint model. So in a joint model, what you do is you're combining all these trajectories. This whole trajectory of each individual is captured, and that is what you are taking it as one of the inputs and then relating it with your time to event as your outcome. Okay, so again here it's only time to event. The only additional step we are doing is we are capturing that progression, that trajectory of each individual, so that we know what is the true underlying the change that is happening for the individual, and trying to see how much is the time to event or what is the probability of survival or transit. Okay. Yes. So the hazard, what you do when you don't do this one, what happens is if you assume it's the same probability, right? So you're actually underestimating your true progression. It depends, because if it's a kind of an outcome where increasing is better, then you will, so it's in the opposite direction. If you especially for here CD4 count, if you don't do this way, you are actually giving a lower hazard rate in comparison to what is really happening. Okay, you're underestimating your hazard rates. But if you don't capture this, are you following? It's a very simple thing, right? So if you don't do the right trajectory, you are giving, let's say for example, if your hazard rate was supposed to be 2, you would have said it is 2.4, something like that, if you don't do the joint model. Okay. Having a joint model method, you will use to address this problem with the extended terms. I think so, because I think afterwards only they realize that probably this is not the way, and that's why you have the joint model, which is addressing how that real capturing of the CD4 decline is taken into. If the CD4 count didn't persistently drop, if it went down and then up again, still you can capture it, because that's what I'm saying. When you do a regression, okay, Ideally, that is what you're doing. So for the first individual, let's say he went down and then suddenly it rose up. Still, you're capturing that progression, and that is what you're incorporating into your joint model, right? So for each individual, you're taking that into account. You're not losing anything. So that's why your hazard rates, if you do the joint model, they are the appropriate ones. You rather either underestimate or overestimate if you don't do the joint model.
Yeah. Hazard rate. Now we give you one hazard rate. So it goes down and then up again.
Yeah.
Or it goes up and
no,
then
no.
down.
What
Which is the hazard rate? Like what would you get that hazard rate as? Would it be like a mean or a median, or would it be, am I making sense?
Yeah, I understand what you're saying. So
that progression, what would your hazard rate fall into?
No. See, what you are confused is with you won't get a different hazard rate for. Ideally, what we are trying to say here is what is your objective? Your objective is to see what is the level of CD4 count that has the effect on your probability of survival. That is what you have to answer. Okay, so here again, the main research question is time to event. How is the CD4 count, which is changing over time, how does it got to do on your survival probability, or what is the risk of dying for that particular patient? So when you're talking about that, what you're capturing in terms of the CD4 change is the true capturing of your data, because you know that a particular patient is decreased suddenly and then suddenly got it increased, rather than having a step function that you assume in your previous model. Yeah?
It is a Cox proportional hazard model. So it is, you don't look at the hazard at a particular point in time. The assumption is as it increases over, the ratio of the two hazards, two individual as compared to male, as compared to someone, the ratio remains constant. The hazard goes up and down, but the other person who are comparing with will also have the same pattern. Therefore, the ratio of the two hazard remains same anywhere. Do you understand what we are saying? We can't discuss it last time. To show you this is we read any basic papers. No. See, for an example, this is time-dependent covariate is something which she started off with. Time-dependent covariate, I remember I told you that when you measure serum creatinine every week or every month over a period of time, we did not have the strategy to analyze, use that information in the analysis. Therefore, say for example, month 1, month 2, month 12, and the event outcome. So I have this information. What I'll do is I'll take this information and correlate it with the event. Okay, supposing this event happened earlier for this person, maybe here, then I'll correlate that. The latest observation which was measured is correlated with the outcome. That is time dependent covariate. Now you have a situation that we can use the whole information for this individual, this much of information, this individual, this much of information, using some kind of model. So instead of taking one, you take the whole sequence of the data and summarize it, synthesize it using the random effect model morning we did, measuring the clustering effect of it and so on and so forth, and put it in the survival analysis. Still, the survival analysis is a Cox proportional hazard model. So the Cox proportional hazard model, say for example, I synthesize this information, which gives me the value of some value, say for example, 10. I get this information, 10 value, and put this information in the Cox model, Cox pH model. there's some values. Another individual, it may be 5.
Yeah.
You understand?
My question actually was, sir, these are all following one linear change from up to down. So my question was, if it's going up, down, up, it's not following the same pattern. One person, the second person here is going up, down, up. That is, in reality, we get values like that also. Up, down, up. You get all of these are negative values. So you can definitely say minus 10 is greater than minus 1.7. But if it's up, down, up, your cumulative values will be different.
Right.
So does it still fall in this same, can you still categorize?
That is a good question. Can't. What she is asking is that she is aware of the proportionality assumption. But she's saying one individual has a pattern like this, another individual has a pattern like this. But we are summarizing the whole pattern and say it is linear or whatever. Is that a right assumption?
Yeah, so usually make the assumption, hoping that the assumption is true. And the modeling is most efficient when that assumption is met. It's like an every regression model. Now, when the assumption is not met, if it is slight departures from the assumption, the model is very robust. It's likely to be not having major impact on the result. If the departure from the assumption is dramatic, you may have a strong impact on it. So that's why we assess the proportionality assumption to see if it's more or less is okay. And if it's more or less okay, then we feel comfortable. If, however, we're having that the ratio is not proportional, so that one is going like this and the other one is going like that, then you're probably not getting valid results. And so therefore, there are other ways to deal with it. You can look at other things. You can not use the semi-parametric proportional hazards. You can use a parametric proportional hazards. You can now look at other parameters like the restricted means survival time. So there are other ways to deal with it, or put in time-dependent covariates.
Take the snapshot where it is all going down versus the point where it's going up again.
No, no.
No, 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 no.
No, 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 no. You validate whether the data has fit the model. So if it is not, that this is not the right model for the data.
Change the model.
Change the model. So
That means all your data has to be in one direction. It never happens that all your data is always
Never.
going in one direction. There's no serial fall. Like if you're looking at serial fall, that's one thing. But your preeminent value will never go from 2 to,
No, that's see, yeah, what you're saying is right. This is a case in any regression. Even if you just do a linear regression also, there may be one patient who started off very late, I mean very high, and then dropped down suddenly, and there may be a patient who's stable all through the time points. But what you're giving as a regression coefficient is the average of all the things. It's the same thing here also, except that the way you capture the projection is you're doing it in terms of a true underlying risk for that patient, and you're not trying to say for everybody between 0 to 6 months it's only 590 or 600. No, sir, I think that it's the problem in any regression for that sake, whether it is Cox or.
So actually, I mean, we're mixing three things here. We're mixing the trajectory of the CD4 count or whatever biomarker you have. We're mixing in the time to a terminal event as a second process that you're interested in. But the third thing we're mixing in is that the trajectory of that biomarker is not fully known. That's the complication that she's looking at it here right now. So there's three things that are going on simultaneously here.
So because what is really, I mean, what the joint, I'm not the one who invented this joint model. I'm just telling you. So what they are trying to say is that the joint model is that the trajectory that you're capturing, you're trying to do as true as possible. That's what we want to see, right? We don't want to do, so the models are being, generated better than the one before is only because you have some drawbacks and then you're trying to make them better so that they reflect the reality. So the reality is that your CD4 count should change for each individual, which you have not looked at in your previous models. And that's what you're trying to say to make your prediction better. Okay, that's all.
Finally, how do the results come?
Results will just be your hazard rate. So now when you see, you will say, so if you do, you can do this, okay? You just do a time dependent model. You run your joint model. You will see that hazard ratios are different. Okay, that's all. But these hazard ratios are supposed to be better because you have considered that projection which caused the change in your hazard. No, it depends on your research question. Now, if I would not say you have to do a joint. If your research question is you have a biomarker which is collected over time, like the CD4, no, that's what I'm saying. No, it depends on your research question. If your research question does not involve any biomarker which is changing over time, you don't have to look at joint model. You don't have to even know about joint models.
You have a biomarker. You have a lab, for example, even with death from heart failure.
Yes.
You can always calculate it.
Yeah.
Any question will have a current.
Okay, but if your research question, your primary question is you are interested in finding out the relationship of that biomarker change on your time to event, then you have to do a joint model. If you have one of your research questions like that, then you do a joint model. But if that's not your aim, then you don't do it. It's all on your objective. You should not forget your objective. If one of your objective is a biomarker effect on the hazard or the probability of survival, then you do the joint.
That's not feature.
The time dependent covariates, we were not able to take all the readings and put it in the model. We remember that is why we took the latest one, closest to the event which has happened. Yeah, we have not done that. So we were not able, in science for quite some time, we were not able to do that. That is why it is called time dependent covariate, that covariate values, creatinine and value, which was measured closer to this event, discharge or death. Now, this latent class model, this giant model, it allows you to summarize the serial measurements and put it as a value in the survival analysis. That is the difference. You should not say lab values. Lab values associated with the serial measurements. Month 1, month 2, month 3, month 4. And do you want to use all that information in the analysis? Then you should use joint model. Suppose if you have one lab values like cholesterol level or whatever, then you don't need giant model. Just any other Cox proportional hazard model, you can do it.
Does that mean that if for ID number 1, I'm having an event captured at 1/7, with the time varying thing, I will able to use the month 6 record, 520. But with the joint modeling, I'm able to use 0.6 into a clock.
Yeah, yes, exactly.
Because that's how the time dependent covariate is modeled. It will only take the one which is the closest to your event. But this one takes everything.
Every observation.
Observation is taken. It's always in any research. It's always good to use all the observations, right? You have taken an effort to collect them. You have to use them. Okay, so that's.
But here there's no comparator. It's only one graph.
No. You can do that comparator.
So you can
do that.
But here, what would be the comparator?
No, we are giving you the concept. In the modeling, you can bring in the comparator. The modeling, you can bring in the diabetes versus non.
Even hazard ratio, if you're comparing two different groups, right?
Here also it's the same thing, right? So for example, you're talking about each so if you talk about this alone, you're saying in change in the CD4 count, that will be your change. That is the one you're comparing. Like in regression, when you have age and weight, for example, what are you saying? For 1 unit increase in the age, the weight is the same thing here. The comparison is between the count, each count of CD4. Okay.
I don't know whether he understood that one. See, compare. No. He is asking. comparator means diabetes mellitus patients versus, wait, DM versus non-DM. So he's saying the DM patients have their own profile, non-DM has their own profile. You can compare it. You can compare it. The challenge is you measure involve all this information into the data. That is
No, see, one thing, please remember, comparison is not only done between categorical variables. It's not like that. Okay, comparison can be done between CD4 count 20 with 21 also as a comparison. Okay, that you should not forget. So you can do a comparison even between the two counts of CD4, right? So here, that's what is the comparison.
So are we summarizing the effect of time on CD4 into a factor that affects the?
Yes.
This
So
is the summary of that information that affects.
that's all. Very simply put, it's just the summary of all the trajectory of all the individuals.
We are not writing each trajectory, which may be very different from some patients might be like at the end of that summary. That summary is not indicative of every patient. It is indicative of.
But at least better than, yeah, but better than the previous models. That is what we're trying to say. Yeah. Yes. Yeah.
But the problem with this would be if you have the mean of a high, low, high would be somewhere in the middle. The mean of a middle would still be middle. So the values that you're getting here, if that's your pattern or that's your pattern, is still the same.
It's the same even in any regression. That is what it is. That's what I'm trying to say. Even if you do a simple regression, if one value is very high, another value is very low, still you're getting only the mean. Mean is your regression coefficient. So it's going to be the same. But what we're trying to say is the way you capture the trajectory is better than what you had been doing so far in your previous models. Okay.
The problem is when you look at that from a clinical perspective, if your CD4 is high, you're less likely to die.
Yes.
If your CD4 is low, you're more likely to die. And then at the end, you say this person with the high CD4 and the low CD4 has an average chance of dying. But actually, it's really, that's not the case at all.
You're not saying that. You're saying that what you're trying to say is CD4, changing of CD4 impacts your chance of dying, your hazard of dying. And time also has to do with your chance of dying. We're doing those two things together. So think about it. Suppose I wanted to not do a joint model. I was very simplistic and I don't have the CD4. What do I have? I have people that are dying. That's all I have. So I will try to understand the time to death and maybe I have some intervention. So I have intervention and I have intervention group and another intervention group, or I have something. So I just want to look at what is the time to dying. Let's ignore an intervention. No intervention. I have a group of people. What I'm interested in, understanding their survival curve. So I can get a Kaplan-Meier survival curve, or I can do a Cox model on their survival curve. And so I just get what it is and I get their hazard ratio. But then somebody tell me, wait a second, you have additional information. Somebody has their CD4. CD4 is related to chance of dying. So can I use their CD4? Yes, use their CD4. What do? If you only have one CD4 at baseline, you use that one CD4. Some people have it high, some people have it low. But on average, you want to see what does the CD4 predict. So you incorporate that into your Cox model. But that's not a good one because you only have one CD4. Now, somebody says, oh, no, we have actually measured it multiple times. So let's get it multiple times. But multiple times, not everybody has the multiple times, and the gaps between them are different. So what do? So we try to make it so that everybody has the data complete on CD4 count. But my ultimate interest is what is happening to time to survival. So all we're doing here is completing the information, getting more value out of the CD4 than having only one or having a few here. We're having all of them and trying to complete it. So we have the CD4 process that we're trying to do, but the ultimate goal is studying the time to survival. That's what we're trying to do. So you're worried about this. This is just almost like completing the data than CD4. They just get in all of those, the proper trajectory of CD4. To get the trajectory of CD4 to help us understand the time to get in the event. That makes sense?
Yeah, absolutely. So basically, we are trying to use all the information that we have so that we are making to make it a better sense to interpret our time to event. You got- You can take it anyway. You can. That's what I'm saying. Even if different time points, still you can use them. It need not be the same time points.
Terminal event, I will be able to take the information after the event has been recorded. And is a terminal one, I will be able to use everything before it.
My terminal and non-terminal, there's nothing to do. Yeah.
Data afterwards to predict what happened earlier. Is that what you're trying to do?
So let's say that I have a secondary outcome which is only a heart rate. People will be living after having a heart rate, and they will be invested. So if that heart rate happens for ID1 at month 6, but I have the
CD4.
recorded at month 12, I won't be using that.
Yeah, but yeah, because it doesn't make sense. Why would the CD4 at month 12 help me predict their outcome at 6 months? That doesn't make sense. You're censored. Once that event occurs, that's it. You're not following this person anymore.
That's the event of interest.
Yeah.
That's one. That's all I have, but now we can do the practical. So just that. So I maybe, and this can also be extended to competing risk. I'm just going to show you how the competing risk changes because this is already done. So ideally, when you don't do a joint model, this is what you end up with. So this is the one that you will actually say that the hazard rate is 1.1. But ideally, if you do a joint model and you capture that trajectory, it's the true underlying risk is 1.16. So you're losing on that component. That's all.
Maybe you have to explain it.
No, because that's the same competing risk. I mean, in terms, so earlier what I was talking about is if you have a time to event, just one event, right? But sometimes you can also extend this joint model for a competing event. So you remember if the competing event was like you had
Sequence of data,
after that only we come to this. Oh, I mean, oh yeah, that I'm not covering. I mean, they are. Okay. Okay. I think Sir covered it because he said about the random effects model.
See, for example, just put the slide. This is the previous slide. Random intercept model. This is a random. Next one.
Yeah, I just have only the.
Yeah. When you have a repeated measures data, so for example, each individual cholesterol level is measured, creatinine level is measured over a period of time. How do we summarize it? We said morning there's a clustering information data. Within the individual, there's a clustering going on. That we said we don't use cluster analysis to do that, but this is a regression analysis in which we capture this, the clustering information. This is called a random intercept model. What do you mean by random intercept model? I think we ran a few times. This is repeated measures data analysis. It's a repeated measures. What we do is we allow each one to have a different starting point. I am allowed to start with a very high level of cholesterol and go on like that. Another person with a low level of cholesterol and go on like that. So it is a different intercept. Okay. So I start off with a high level, therefore my intercept is very high. Another person and so on and so forth. We measure the variability of these intercepts. That is called the intra-class correlation coefficient in research. That tells you how much correlation going on in the repeated measure structure. That is one value which tells you whether the information is correlated or not. So this is very important. This is the structure you capture for joint model. This is one piece, one process which Kant was talking about it in the morning. And in the process, you capture this information and put it in the survival analysis, Cox proportional hazard model. This is the second process. So here, you see the slope, everybody has the same slope. Do you understand this one? The slope is the rate of change is same. I can start off with this level, she can start off with this level, but the slope is same. Slope is constant everywhere, but you allow the slope also to change. Then it becomes random intercept and random slope model. This is what you are talking about. Some people have different values and so on and so forth. And synthesize that information and put that information into the joint model. This is the first process. Okay, is that right?
But again, what you meant, that's right. But
This is linear. Again, this is linear.
Linear.
My question is if it's not linear.
anything, but still you're giving an average effect.
Average,
So that's what you will end up with. You get only one regression coefficient.
But it's not good. That's not very good if you don't
But
have a
it's
linear
better
model,
than
but it's
the
better
previous
than the
model.
previous
That's
one.
all.
Yeah. This is a random slope model. So random intercept, everybody starts with a different level and different slopes. So synthesize this information and put it in the joint model. Okay.
Because I thought sir already covered, so this is the only thing that. Yeah, and joint models can be extended even to multi-state models. That's what I saw just now, but I'm not very sure how to do that, sir. So it seems you can extend your joint models to like extended Cox and even yeah, because what you're capturing is only that trajectory and incorporating that into your. Any other?
Even though you're measuring it by alpha.
This is my faculty that I wouldn't have even observed that. This is just my, just to show that you will also have other covariates that you will measure. What I wanted to show another, like how this, you saw Chance's slide. He said that alpha was the one which talks about the change, the effect of the biomarker on the survival probability, right? So that is the one which talks about your hazard rates. So basically, what it does is in the back end the back end of the way it works in the computer is, so let's say for example this is what you have, like I mentioned, for each patient you capture the change that is happening, right? So that is what you have. Now what it does is okay, so basically it starts off with assuming that the hazard is minus 0.01, so alpha is minus 0.01, and then it calculates these the hazard rates, okay, to see, for example, let's say, okay, first let's assume alpha is 0, okay, alpha is here, this one, we talk about this one, alpha is 0. When this becomes 0, what was it going to be? The hi of t is nothing but the baseline, right? These two are the same, but ideally, can you assume that? That's not true. So, and then also looking at your data, you know that there should be a decreasing, but not the same, right? So then what it does is it again takes the next value of minus 0.01. So this is how it, builds in the back end. And then finally, you'll end up with these points and it will take the one which is the maximum. That's your likelihood estimate of alpha, which talks about on an average, what is the risk of dying given this trajectory of CD4 count. So that's what you get, one alpha value, okay, which talks about the effect of CD4 on the hazards, on the survival probability. I mean, for any regression, this is how it